In the first two videos, we covered how the intermediate representation is created, and then kind of a very fast overview of how transpilation happens, and the data structures that are used during transpilation. And in this video, I think I'm going to cover the expressions, type names, and types, and show the visitors. So, as you may remember, all of the types that are used in the transpiler have no member functions. So they are just essentially data, and I declare functions outside the class. So in C++, those are called free functions as opposed to member functions, and it's generally preferable to have free functions. So I just went with that guideline, and essentially I don't have any member functions. Now the biggest difference with this and object-oriented is that I also don't have inheritance, and so when you have a type which has different alternatives to it, which in OOP would be classes that inherit from it. So you can imagine if this was object-oriented, you would have an interface statement, and you would have these classes extending the statement abstract class or interface, and they would override the methods from the interface, right? Or the virtual member functions in C++. So what I do instead is that the statement is a struct, which is, it just holds a variant of the alternatives. And when I want to define a function on it, on that takes any of these alternatives, you use essentially standard visit over the standard variant. So I can show you, for example, I want statement visitor. So I make a visitor, which is templated with the type of the visitor. I'm using CRTP, curiously recurring template pattern, or curiously recursive template pattern, I can't remember. And so I use deducing this to call the visitor, so that essentially the operator, the call operator of the statement visitor with a statement returned standard visit call operator of the visitor. You don't need to get the details, essentially, just know that it's basically the visitor pattern for standard variant and this like hierarchy that I'm using. Now what that means is that I can define for example, a transpile statement visitor. It extends statement visitor templated with itself. It uses the call operator from the statement visitor. It has some data, such as the state, variables, expected return type, and the return type is declared here. And here I have the declarations of the call operators. Now if you go down here, you see statement visitor declarations, and it's here. And so when I add a new type of statement, I just have to add it here. Obviously, I also have to add it here. And it's going to get added in all of the visitors which have this macro here. And then I define a function such as transpile statement. So I have the transpile statement visitor type, I have the transpile statement function. I here have the state variables statement that I put the state variables. I'm not sure why. So it might be preferable to swap these two arguments order, but anyway. I did what I did. Originally this was not here and I added it as the last argument, but I think it might be preferable to move it up. I just instantiate the visitor with the default constructor for the base class, state variables, return type. and I apply the call operator with the statement. Now, if the statement is a const node struct statement, it's going to use this operator, and it's going to call statement. It's going to call visit. If it's a concrete type, it's going to match one of these declarations here. So if I call it with an I for statement or an if statement or a for statement, I'm not going to have to do the visit. But most of the time, of course, you're calling it with just a statement, and you have to do the visit to know what you're dealing with. Now, if I go into the implementation, you can see for each type of statement, I just transpile like, for example here, right, the while statement, it's going to return while plus, well, maybe I shouldn't call these like S1. Let me rename. So every time I have a variable that has a short name, it's because I didn't know what to call it at the time, and I just wanted to save time. But in the end, I can spot them pretty easily because they have a short name and just rename them. So I can rename this to while expr info, and this to while expr info OK. And S2 is the statements, let's call them transpiled statements. It could be the while body or something, but anyway, right? So basically you transpile the condition, right? So this is the condition, while expr. And then, so when you transpile, do while, open parentheses, expression, and then open and put the statements, right? So this is quite simple. Also because the return type of the transpile statement visitor is an expected string. So you can see, for example, this expr info, this is a transpile expression information T. This is not a string. And if it has an error, I return the error here. So basically, if one of these steps produces an error, I'm going to return an unexpected. If I make it to the end, I return the expected string value. Most of my functions have an expected return type, like standard expected, and I do not have any exceptions in my code. I do have like throw. Throw in my code just means not implemented. So yeah, that's the explanations for the statement. Now, if we look at this, there's other instances of variant in my, let's search here. In my node structs file. So for example, metatype is one that I want to cover, and type name is another one. So as you can see, type name, it's either a template type name, namespace, base, or union. So essentially, a base type name is something like A union type name is something like A or B, namespace type name is something like AB, and template type name is something like AB like this. So it's extremely similar to C++, except for the fact that C++ doesn't have a union built in the language. And now let me go back. There's another one, it's the expression that I just had here. Struct expression. The expressions, this is the one that has the most alternatives. So if you have like a string, it's a token string. If you have a number, like 1, 2, 3, you get an integer number, 123.456. You'd get a floating point number. If you have the name of a variable or the name of anything really, some identifier, it's going to be a string, not a token string. A token string is the one that's an actual string. This one is like an identifier. Then the other types of expressions, so brace arguments is something like this. Parent arguments is something like this. Property access expression is something like a.b. Access and call is like a.b call. And I do have to make a distinction because I do something weird with the functions where you can call a free function. Imagine you have a free function f of a, b. Instead, you can do a.fb. And so f is not a member of a. So it's way better for me if I group all of this together so that I can make sense of it more easily. Then there's the bracket access expression, so something like a bracket b. Construct is like t with arguments inside. Template expression, I'm guessing it's something like that. I'm not exactly sure in which scenario it comes in and why it wouldn't be a type name. But as you can see, I do have template expression and namespace expression. There's some areas where a type name can be used instead of an expression, and it's not clear, whether you're dealing with an expression or a type name. So this is the area where there's the most amount of friction in my transpiler right now when I'm writing code, and I'm thinking, could that thing be a type name? And most of the time, I just assume that it can't. So you'll see a bunch of checks in my code. Like if it doesn't hold a non-type information, that's a problem. And typically when you get the, for example here, transpile expression, it returns either like a type information or a non-type information. And you can know, and typically you do expect a non-type information, but sometimes a type information might be there. So it's just that in most cases it can't happen, but for generally speaking, for an expression, it can be a type. Anyway, now a call expression, of course, is just like a with arguments. Unary expression is when you use a unary operator like plus a or minus a or not a. Multiplicative expression, of course, like a times b, now a plus b for additive, a bigger, smaller than b, a equals b for comparison. Actually, no, equality is a equals here. For a sec, I thought it was in compare. Now, and then or, same thing, just like a and b, a or b. And the conditional expression is, it's like in Python, not like it's not a ternary. So it is a ternary, but it's not like, so in C++ we have A, B, C like this. In Python what they do is A is B if A else C, right? To have this thing is equivalent to that, and this is how it is in my language. So it's like 0 if condition else 1. So those are the expressions, and now the other type that I have is the metatype. Metatype. So the metatype, essentially it's used when you have an expression, you're trying to get the type that is represented by the expression. So for example, if you get the type of 1, you get a primitive type, and the primitive type is going to contain int. So if you did like type of 1 will return like a primitive type that points to int, but if you do type of like string 1 to 3, then it's going to be a primitive type string. If you get the type of any like variable or expression that returns a variable or like a value or whatever, then the type is going to point to the actual type of the variable. So there's a node struct type, as you can see. So it's literally like a type has like a name, namespace, aliases. This is like a concrete type. I think there should be like a pointer to it, but for now I'm copying it, but I do have to fix some of these things. A function type, so if you declare a function and then you get the type of that identifier and it points to a function, you get a function type. Same, like if you declare an interface, if you declare a namespace and then you're trying to get the type of that identifier, you'll get an interface, a namespace. Union type, so yeah, if you have a type name, a union type name, and then you get the type of that union type name, you'll get a union type. If you declare a template and you get the type of the template, you get a template type. Built-ins, I won't get into, probably like some of the most confusing things that I have in here, so I don't think I want to get in there. Enum, same thing. If you declare an enum, then you get the type of an instance of, or the name of that enum rather, you get an enum type. Now, if you get the type of an instance of the enum, you get an enum value type. So let me do example enum e, and then when you do type of e, that's what you would get. And here it's example enum e a b, and then if you do type of e a, you get enum value type. And finally aggregate type. Yeah, so this type of A, B, C. So this is, you can't get the actual type of that. It needs to be solved depending on the context. It can make sense or it can't make sense to have an aggregate. And typically the aggregate is used to initialize an object. But you need to know the type of the object that you're trying to instantiate. So at this point, when you're getting the type of this, there is no type to it. It's just an aggregate. And then later on, you check, can I assign this aggregate to the type I'm trying to fit it in? Same thing. If you do type of literally the word vector, so vector, set, and map are handled by the language. You cannot implement them as a user. They are part of the language. You'd get their respective types here, or meta type. And then if you get the type of an instance of those, then you just get like a vector type, set type, and map type. And then if you were to, for example, get the type of map int instance, that would actually return a type here, I believe. But I'm not 100% anymore. We could check. But essentially, when you instantiate a template in my language, it gets fully resolved into a concrete type, and the template doesn't exist anymore. And the type gets added to the state. Now, I have multiple operations over these things, so statement is very simple because the only thing you can do with the statement is to transpile it. Of course, most of these things, like all of these things, they all have a bunch of recursion. So there's statements and statements, there's expressions and expressions, there's type names and type names, there's types and types. So none of the logic is, I want to say, simple, but none of it is really that complicated either. So let's look at, for example, probably an expression. Let's start with expression. So transpile expression. Now the return type of the transpile expression is not a string. It's a expression information, which is either going to be a type or a non-type. It's going to have a representation in C++, a meta type, and if it's a non-type, so if it's an expression, it's going to have a value category. If it's a type, it's not going to have a value category. So if we look at, let's go at the bottom. So these are the simplest ones. So if you are trying to transpile an expression and the expression is like a string token, it's very simple, no error handling, no nothing. The type is a primitive type standard string. The representation is string with the string literal. And the value category is a value. Pretty much the same for int and float. Now, the others are much more complicated. So this one is the most basic because it's literally just an identifier. So basically, when you're trying to transpile an identifier, you check, well, is it a variable? If it's a variable, we get the last variable from the stack. Right now, I'm throwing, if there's more than one variable with the same name, it could make sense if the variables are shadowed and there's one in an outer scope and one in a further, like, indented scope that you're into, then maybe you'd want to use the shadowed variable. Right now I don't support shadowed variables, so I just throw if there's more than one variable with the same name. But anyway, that's kind of a detail. Now, you get the variable that's at that spot. The type is the type of the variable. The representation is the it's literally the identifier. And the value category is going to be a copy of the variable's value category. So a variable's value category is either going to be a reference or mutable reference, depending on whether the variable is declared const or not. It cannot be a value because it's a variable. If you move it, it becomes a value, but you can only move it if it's immutable. Now, well, actually, no, that's not true. You can move it if it's not mutable, but it has to be the last use of that variable in the scope. I don't think, like, if I have branching and stuff, I don't think I'd be able to resolve that. But I do want, because for example in C++ you cannot move const variables, and it's the biggest pain because then it means that you have to declare a bunch of stuff non-const, and it's just more prone to error. So I do want to be able to move const. But of course you need to be able to demonstrate that you're not going to move twice, but you already need to be able to demonstrate that you're not going to move twice as it is, so that's not really an additional problem. Now, if it's a variable, you return the variable. Now, if it's a function, in the global namespace, it can be either a function or a function using auto. Now, if it's either one of those, you return a function type. So the thing is, you need to, I don't return like which function it is, I just return that it is a function, because depending on the arguments that are passed, you're going to need to resolve which function it is, right? Imagine you have a function that takes an int, like f of 1, and a function that takes a string, f of 1 to 3. Well, when you're trying to transpile f, you don't know yet what the arguments are. So all you can say is, look, I know that f is a function, I know what you're trying to do, but I don't know which one it is. It could be that one or that one. We're just going to return the name of the function. Now, it can also be a type. So kind of similar, just return. So if it's a type, as you can see, there's no value category. Same here, no value category if it's a function. So if it's a variable, there's a value category, but if it's a function or a type, no category. If it's an alias, no category. If it's a template, no category, namespace, built-in, enum. And then at the end, I say undeclared variable. Here I should say undeclared identifier, I think. Let's change that to identifier and compile. And I think I do have undeclared identifier. Okay. And another thing I could do is probably rename expr to identifier, but in all of these functions, the expression is just called expr, and I don't think I'm going to go rename all of them. So let's leave that as expr. Now, the other call operators for the different types are pretty similar, like, to each other. Essentially, you're just trying to transpile the expression, and so there's a bunch of logic to check if the expression makes sense, right? But other than that, it's pretty much exactly what you'd expect when you try to transpile. Like imagine if it's a call operator, then you just check, well, do the arguments make sense? And if the arguments don't make sense, you return an error. And if the arguments do make sense, then you return like the representation, the value category of the call, and then the meta type, and it's that simple. So there's nothing really complicated when you're trying to implement one of these blocks, but putting together all of the logic can be hard. But I must say that there's little software design that goes into implementing like any of these things. The hardest thing was coming up with the result type of the call operator, which is either like the type result or the non-type result. At first, both of them were essentially the non-type, and I was dealing with types as if they were values. And at some point I realized, holy, if I separate them, it's going to be so much clearer. And I was right, it is a lot clearer. So now the other ones are like the type visitor, type name visitor. So type name is the most similar to the expression, so we're going to go with that. Actually, let me just check out the other. So as you can see, there's other visitors for expression, right? So we covered transpile expression, but there's other ones like original representation. This one is kind of interesting. It's not implemented fully because I just added it, and I only implement things. I kind of do test-driven development, so if my tests pass, I don't go and change a bunch of code. I try to add a test that fails. And currently there's a test that fails already because I was working on something, so I'm not going to start moving things around here. Though, the goal of this expression is to, when you give an error to the user, to say, this bit of code that you wrote is incorrect, you call the expression original representation, and it produces a Caesium code that was used in this expression. So it doesn't transpile the expression to C++ to give an error, right? It gives you back the original code that you wrote. But it doesn't actually give you back the code that you wrote. It might be formatted differently, but other than that, it will be the same code that you wrote. It's just not formatted the same way. So I don't look through the file to like look at the actual tokens that were written. I recreate them. There's advantages and disadvantages, so of course it's always formatted the same way here. Might be a little bit harder for the user to make sense of it, but at the same time, I think it's going to be fine, but I've only used it for simple expressions. Like for example, I can show you, is it this one? Yeah, so here I have a little example that I have where I'm trying to select, I have a template with no specialized args, one where t is equal to string, one where u is equal to int, and then I try to get the template for string int, and of course there's a conflict, it can't pick between these two. And then the error says, hey, I couldn't pick between problematic t equals string and problematic u equals int. So I used the original representation to produce this thing here. I mean, that's such a detail, it probably doesn't even make sense in the context I'm presenting it in, but I thought I'd give like a little bit of an example, but you know, it's typically this is only used for giving error messages is what I'm trying to get at. Now, the other one, expression for template, is essentially, I don't transpile templates into C++, I expand them before. And so I try to always do that the same way. But right now, this is absolutely one of the worst parts of the transpiler is that the way that the template names are produced is absolutely terrible. I don't even know if any of this code is getting called, and there's a lot of conflict between this and the type name wait, where is it? Here I have type name for template. This is kind of hell, and I do have to do something about it, but right now the things are getting transpiled properly and they are getting the same name, so I didn't bother checking that. But anyway, so that's it for the expression visitors. Now the type names, I have type name for template, I have transpile type name, which is essentially used exactly like the transpile expression type, except I do believe that this is not. So this is just a transpile T. So when you transpile a type name, you know that you always get a type. So I also actually have a type of type name. So if I'm trying to get the type, I do type of type name, and if I'm trying to transpile, I do transpile type name. So often you'll see both paired up, and there is a little bit of work that is duplicated, I imagine, between these two things. Yeah, like there is 100% duplicated work, but at the same time, this is so simple because there's only 4 different type names that this is not that big of a problem. I had a similar problem with the expressions where I was getting the type, getting the value category, getting the representation, and I was duplicating a lot of work. But here I don't mind duplicating these 2 files, that's very minimal. Now, type template of type name. What is that? Namespace, union, template. Yeah, so I think this is called when you have a type name and you're trying to check, it's being used like a template, and you just want to verify that it can be used like a template. So if it's like a vector set or map, it can. If it's a variant, it can. Otherwise, if it's an actual template that you find in the global namespace or whatever, then yeah, that's good. Now, what are the other ones? So type name for template is just for the transpilation, expansion, name expansion. Type name original representation, exactly like the expression. We're just trying to produce the original representation as closely as possible for the user to make sense of the code, of the error rather. And probably the most complicated part of the transpiler to understand is the types, and they're actually not that bad, I feel. But so basically, this is an example of a. Well, first of all, right, you see in the type name, I have the type of type name, which you pass a type name and it returns a meta type. For example, so if it's a union type name, it returns a union type, right? And now if you have a type and you do type name of type and you have a union type, then you get a union type name. So you quite often you need to go, not, I don't want to say back and forth, but yeah, pretty much you do end up going back and forth. But not in the same scope. Now, that's probably the simplest one, right? The transferring between types and type names. Then there's different operations that can be called on types, such as a member call, function call like with args, type of postfix, and type of resolution operator. So the resolution operator is the namespace operator, colon colon. So essentially, like if it's a namespace type, you look through the types, the aliases, interfaces of the namespace, and you return whatever you find. If it's any other type, that operation doesn't make sense. Now, same for type of postfix member visitor. So this is like if you do a.b. So if the type of a is just a regular type, you just check essentially is b one of the member variables of the type. If so, you return like the member variable. If not, well, you say type of object of type has no member property name, right? If it's a primitive type, like an int, if you do like 1.b, this is obviously not correct. If it's a function, so if you do like f.x, like you cannot do that. If it's an interface, that's quite interesting. So an interface is like a union of types. And so you look through each of the members of the interfaces if they have that member. And if they do, then you return that. But they need to all have it. Now vector, as you can see, there's commented code here. For example, the push is a member of the vector, right? But push is a function call. So what happens is that it doesn't actually get found in the type of postfix member. It's found in the member call, transpile member call. So if I look for vector type here, you can see that I have push here. So if you have a like v.push call arguments, and v is a vector type, then this is going to match this path here. Property name equals push, and it's going to check, well, can you push that wrong type push to vector? Here you see I put t. I need to use the type name original representation instead of t. So some of my error messages are not up to date. And then finally I have, for example, type of function call like with args. So if it's a type, you cannot call it like a function. If it's a primitive, you can't. But if it's a function type, you can, except right now I don't do that apparently. I guess maybe this is dead code, by the way. And finally I have like traverse type. So this just adds the types to the traversed, and if it's like a union, it adds all of them to the traversed or something, right? So nothing too complicated. So I think that will be it for the explanations of the expressions, type names, and types.